Today, I'll talk about topological tracking for mobility support robots based on multi-scale batch learning growing neural gas. Recently, the basic concept of cyber-physical systems has been extended to various research fields, such as cyber-physical social systems and cyber-physical human systems. And thanks to the rapid progress of networks technology, we can realize the real-time measurement of people, moving objects, and environments in a wide area. However, it is difficult to simulate and analyze the interaction because we must simultaneously deal with quantitatively different big data. In order to simulate real-world phenomena in the cyber world, we often have to extract features and structures based on graph theory and topology. Therefore, we propose the concept of a topological twin. This figure shows the concept of topological twin in cyber-physical social systems. We can extract topological features from big data as topological big data at various levels. The methodology on topological mapping, including growing neural gas, is helpful to extract topological features hidden in big data. We can apply the obtained topological structure to inference, search, and prediction based on graph theory and network science. In this paper, we propose a prediction method using the adjacent matrix of the topological structure obtained by multi-scale batch learning growing neural gas and apply it to the analysis of topological tracking in the navigation task of a mobile assistive robot. We need a multi-scopic approach to deal with inference, learning, search, and prediction based on topological and graphical data as the methodology of topological intelligence. In microscopic simulation, we can deal with the dynamics inside object and internal state with the highest resolution and shortest time interval in intimate and inside space. In the Mesoscopic simulation, we deal with approximated rigid body dynamics between several objects in the surrounding environment of human and robots, such as personal space. In the macroscopic simulation, we deal with spatio-temporal relationships between objects without using dynamic simulations in public or social space. In order to connect multi-scopic simulation, we need topological or graphical structures for the essential analysis without using all data. In this paper, we focus on the macroscopic analysis based on a mesoscopic simulation of mobility support robots. We assume people and robots in the mesoscopic simulation, and we use two types of mobility support robots: electric wheelchairs and robot-assist walkers. Each person and robot can take multi-objective behaviors of collision avoidance and target tracking by using fuzzy control. The position data of human and robots measured in the mesoscopic simulation are transferred to the macroscopic simulation through TCP/IP communication, and we use GNG to extract topological structures for multi-scopic simulation. Multi-scale batch learning GNG is designed to increase the learning efficiency of regular GNG, allowing them to run faster. Specifically, we start with a small batch of the entire data. In this case, we start 1/8 of all data, and gradually increase to 1/4 and half, and finally all the data is used. And we also increase the number of nodes accordingly. By starting with a small amount of data at the beginning and gradually increasing the amount, the GNG is able to achieve faster and highly efficient running. Initially, it tried to cover the entire dataset in a rough way, and in the final stage, it can use the entire dataset to extract detailed and topological structures. Next, we will discuss our proposed system. The system using an adjacent matrix. We will apply graph theory to the extracted topological structure. First, let's look at the adjacent matrix. This matrix is 1 if there is an edge between two nodes on the graph, and 0 if there is not. We can use this adjacent matrix to find the nodes that can be reached in k times moves from a point. If the adjacent matrix is A, it is expressed as A to the kth power. Then the following equation expresses the combination Sk that will reach a node within k times. Let's check the prediction of the proposed system using a simple simulation. The figure on the left is a simple example of a simulation in which a person and an MSR go back and forth between two targets. The figure on the right shows the trajectories of the human and MSR actions. The figure on the left shows the topological structure extracted from the movement trajectory obtained in using multi-scale batch learning GNG. The next figure on the right shows the result of prediction, the range of possible action by the adjacent matrix. In this figure, the red nodes indicate the range that can be reached in two moves, which is the square of A. However, the moving direction shown in the figure is not clear from the viewpoint of visualization. Because the previous equation did not include the effect of the time direction, but in reality, MSR is likely to continue in the direction it has been going, so we will include them in the calculation. We have two vectors. An agent is present at the node, the corresponding element of H set 1, if not multiplied by the discount rate gamma. Then, using U calculated by these methods, behavior prediction considering the direction of movement is performed. The behavior prediction result V is expressed by the following equation. Next, we check the behavior of the system on the simple simulation shown before. First, look at the figure above. In the Mesoscopic simulation, the person and the MSR are getting closer, but they are still some distance apart. If you check the Macroscopic simulation at this time, we will see that the nodes in the direction the MSR is moving are shown in red. which indicates that predict the possible moving direction from the previous path is being performed. In the figure below, the person and MSR are approaching each other. In this case, the MSR, of course, cannot move in the direction of the person. However, if you check the macroscopic simulation, you will see that the MSR can move in the direction of the person and is marked as the red nodes. So we update the model to take into account the movement of other agents. Set nodes that are adjacent to other agent to negative values. Here we use the estimated direction of possible movement for other agent, and the equation is as follows. The result of the simulation using the update equation is shown below. The adjacent nodes of the MSR are shown in red, and those with a negative value are in yellow. In the above figure, the person and the MSR are far enough apart that the prediction works as well as it is in the previous case. Next, look at the figure below. In the mesoscopic simulation, the person and the MSR are close together, and the MSR's direction of travel is blocked. But in the macroscopic simulation, the adjacent node in color shows that moving direction for collision avoidance with other agent. In this section, we show a simulation result of topological tracking based on the proposed method. The number of maximal nodes in MSBL GNG is 320, and the number of training data is 6,400. The numbers of people and MSR are 4 and 2. The figure on the right shows the mesoscopic simulation. 4 person and 2 MSR randomly move to one of 4 target points. The figure on the left is a macroscopic simulation. Here we can see that we are able to extract the topological structure from the MSR and human trajectory using multi-scale batch learning GNG. This is the result of the simulation. We can see in the mesoscopic simulation the current position of MSR and person. Then, on the macroscopic simulation, adjacent nodes and selected nodes are in red, and nodes with a negative value are in yellow. We can easily understand the current situation of MSR with other agents. Conclusion. In this research, proposed an analysis method of macroscopic topological tracking based on multi-scale batch learning growing neural gas. We discussed how to use the adjacent matrix obtained by the connectivity of nodes in topological mapping to discuss the prediction in human and robot tracking. Then we showed the effectiveness of the proposed analysis method through several simulation results. In future work, we will compare the computational cost and accuracy of the proposed method with stochastic simulations, and we will apply the proposed method to temporal target generation in the macroscopic simulation to realize the collision avoidance in the mesoscopic simulation. In this way, we can discuss the meso-macro loop based on the bottom-up construction and top-down constraint in the multi-scopic simulations. Thank you for your attention.